What will the next symbol be? It sounds almost too simple to be interesting. You are handed a sequence, one symbol after another. Bits in a file, words in a sentence, prices ticking by in a market. Each symbol is drawn from some fixed alphabet. The set of things that can occur. And your job is just this, having seen everything up to now, say what comes next. That one question, asked over and over, turns out to sit underneath a startling amount of modern computing.
Why would one little question matter that much?
Because so many problems are secretly this problem in disguise. Compression is next symbol prediction. The better you guess what is coming, the fewer bits you need to write it down. A language model is next symbol prediction. Every large model behind the chat assistants is, at heart, a next token predictor. Forecasting a market, flagging a fraudulent transaction, letting an agent imagine the consequence of an action, all of them come back to guessing the next term of a sequence. Solve prediction well, and a whole family of problems falls at once. Now here is the first real idea, and it is easy to miss. A good predictor does not blurt out a single guess. The next bit is a 1, and then stop. It reports a probability distribution. Over the whole alphabet, how likely each possible next symbol is. For a stream of bits, that collapses to a single number, the probability that the next bit is a 1. Why insist on a distribution instead of a guess? Because a distribution can be honest about its own uncertainty. It can be calibrated. So that the outcomes you call 70% likely really do happen, about 70% of the time. We are not predicting the future. We are quantifying our uncertainty about it. If a prediction is a probability distribution, how do we grade it? We want a score that rewards honesty, one that is best served by reporting exactly what you truly believe. Here is the rule. When the real next symbol arrives, look at the probability you had assigned to that outcome, and take the negative logarithm of it. That number is your loss. On this symbol, low probability on the thing that actually happened means a large penalty. High probability means almost none. Add it up over the whole sequence, and you have measured your total surprise.
Why the logarithm, though? Why not just penalize by how far off the probability was?
2 reasons, and they run deep. First, the negative logarithm of the probability is exactly the number of bits an ideal code would spend on that outcome. So your score is measured in bits of surprise. We will come straight back to that, because it is the whole next idea. Second, this score is what statisticians call a proper scoring rule. On average, it is smallest precisely when the probabilities you report equal the true probabilities. Hedge or bluff with false confidence, and the log loss charges you for it. Notice what that rules out. Overconfidence is the real danger here. Assign a probability near 0 to something, and then watch it happen, and the negative logarithm climbs toward infinity. A single confident mistake can dominate your entire score. So the winning strategy is to spread your belief to match reality. Bold where the evidence is strong, humble where it is thin. Predicting well just means assigning high probability to what actually happens. Let me show you why prediction and compression are the same thing. Suppose you have to send one of 4 messages to a friend over a wire that carries only bits. If all 4 are equally likely, you spend 2 bits each, 4 messages, 4 codes of length 2, and there is nothing clever to do. But suppose they are not equally likely. One message turns up half the time, the next a quarter of the time, and the last 2 are rare. Then you can do better with a variable length code. Give the common message a short code, a single bit, and hand the long codes to the messages you almost never send. The average length drops below 2 bits, and over many messages that saving is real.
But if the codes have different lengths, how does my friend know where one ends and the next begins?
Exactly the right worry. The trick is to make the code prefix free, so that no complete code word is the beginning of another one. Then the instant your friend has read a valid code word, they know it is finished, with no separators needed. Picture the codes as a binary tree. each code word a leaf at the end of a path down from the root. And one iron law governs which sets of lengths are even possible. Short code words are expensive. Each one you spend uses up a fixed slice of the tree, and by Craft's inequality, those slices can total at most one. You have a budget, and you cannot overspend it. Now watch the two worlds click together. Take any prefix-free code. The slice of the tree each code word uses is 2 raised to the negative of its length, and by Craft, those slices sum to at most 1. But a list of numbers that are not negative and sum to 1 is exactly a probability distribution. So every code secretly defines a probability. Short code word, high probability; long code word, low probability. And the reverse holds too. Given any probabilities, there is a code whose lengths are essentially the negative logarithm of each probability. Description, length, and probability are one structure seen from two sides. A code is a set of descriptions. A distribution is a set of weights. They are coupled, each one fixing the other.
So my predictor's probabilities can be turned straight into a code.
That is precisely what a compressor does. An arithmetic coder takes the probability your predictor assigns to each next symbol and spends the negative logarithm of that probability, in bits, symbol after symbol. Predict the true distribution, and you reach the shortest possible average length, the limit Shannon proved you could not beat. This is why the strongest compressors on Earth have sophisticated predictors humming away inside them. A predictor is a compressor, and a compressor is a predictor. So far we have talked about how to predict. Now ask the other question: where do sequences even come from? Behind any stream there is some mechanism producing it, and we call that the data generating process. It is just a rule that says, given everything so far, how probable each next symbol is. Knowing the shape of that process is what tells you which predictor to reach for. So it is worth keeping a small ladder of these processes in mind.
Does the process really depend on the entire past? That sounds impossible to pin down.
Often it does not, and that is what makes prediction tractable. The workhorse is the Markov process, where the next symbol depends only on a window of the most recent symbols, not on the whole history. Picture that window sliding along the stream. Each time a new symbol arrives, the window steps forward, and the oldest symbol slips out of memory. You predict what comes next from only the few symbols still inside the window, and everything before them is forgotten. Shrink the window all the way down to a single symbol, and you get the simplest case, a first-order process. A little transition table that says, after a 0, these odds, and after a 1, those. Widen the window to remember more, and you climb to higher orders, but there is a cost. The number of distinct contexts you must track grows as 2 raised to the width of the window. Memory is powerful, and memory is expensive. There is a subtler class sitting just above Markov, called a tree source. The insight is that not every context needs the same depth of memory. Some histories are decisive after a single symbol. Others you have to follow much further before the future comes into focus. A tree source lets each branch stop at its own depth, spending memory only where it pays. So that is the ladder. No memory at all, then a fixed window, then a window that varies with the context. Each rung is a guess about how much of the past actually matters, and a good predictor is really a good guess about the process behind the data. We now have a problem, a way to score it, its link to compression, and a picture of where sequences come from. One piece remains: by what standard do we judge a predictor? Comparing against perfection is unfair, because perfection may be unknowable. So instead, we compare against the best predictor in some honest class of models, and we measure the gap. That gap has a name. It is called regret. How much more you paid, in total log loss over the whole sequence, than the single best model in the class would have paid.
But I do not know which model in the class is best until it is all over. Is low regret even achievable?
Remarkably, yes, and chasing it is the whole game. The prize is sublinear regret. where the total gap grows more slowly than the sequence itself. When that happens, your extra cost per symbol shrinks towards zero as the stream runs on. In the long run, you predict essentially as well as the best model in the class, even though nobody ever told you in advance which one it was. You are, in effect, learning it as you go.
So what is the North Star for the whole series?
Here it is. Make the class of competitors as broad as you dare. Let it be every program a computer could run. The predictor that stays competitive with that class is Solomonoff induction. The theoretical ideal we meet next episode, provably optimal and, as we will see, provably impossible to compute. Every practical method after it, whether context tree weighting, an n-gram model, or a neural network, is an approximation to that ideal, a different bargain between what you can represent and what you can afford. Predict the next symbol, score yourself by your surprise, and chase the best model you can afford to compete with.